Welcome to the lesson video on random forests. In this video, we're going to talk about random forests, which are an ensemble method for building with trees. So an ensemble method, we're going to build lots of trees and then average the result. And in random forest, the particular thing that's used in building these trees, we're going to use bagging. So that means each time we build each individual tree, we're going to take a random subset of original data for training that tree. And then in the creation of that tree, when each node in each tree is created, we do this. We only allow a random subset of the predictor variables. So that's the important thing that we look at when we build our tree. We only allow the node to be created with some random subset. This creates greater variety among the trees, or decorrelates the trees is another way to put it. And this gives us more robustness against overtraining, and it further increases accuracy. And so those are the things we're going to look at in this talk today. So to start with, we have this picture, which should be familiar from the bagging slide. And so this is a picture of the bagging process for building a tree ensemble. And so we start with our original data right up here, and we're going to build some number of decision trees off that original data. And so in this diagram, this arrow says we're going to build our first decision tree. We take a random subset of that original data, and the decision tree is displayed here, displayed by the regions it's going to be classifying with. And so there's a diagram that suggests what this tree might be. Look here as well, a diagram of the tree. And then we go along, we build another tree with a different random subset of data. And remember, in bagging, those random subsets are created with replacement. And then we go through and we create a bunch more until we get all of the trees that we need. And then after we've built all those trees, we create the ensemble predictor, which is the average of those trees. So meaning if a new data point comes in, we would look at the classification assigned to that new data point by all the trees in our ensemble. And for classification, we would take a majority vote. If most of those trees voted that point to be green, we'd call it green. If most of them called it to be red, we'd call it red. If we're doing probabilities for classification, we would look at what fraction of those trees assigned that new point to which class. So if 2/3 of them assigned it to green, the probability for green would be 0.66. Now, we're talking random forest, we make one further modification, and we've talked about when these nodes are created in these trees, only some random subset of the features are allowed for each node. So we make this first node and this first tree on the left. We say we have 10 predictors, we're going to pick a random subset of maybe 6, and only those 6 will be examined to figure out what the best split, meaning which variable to use and what threshold to use for that first node. For the second node, we'll take a different random subset of 6, or it could be the same subset. We'll repeatedly select that random subset each time for each node. This creates more variety and it decorrelates our trees. Now let's talk about the different parameters that have to be selected as you're making a random forest. First thing that has to be selected is our bagging percentage, right? In R, this is called sample size. There's a Microsoft paper on decision trees that you're going to be reading. And so we're going to use some of the figures and talk about that Microsoft paper. So anywhere you see MS paper, that's the Microsoft paper that you read for decision trees. And now we're going to talk about decision forests. You're going to read the second part. And so that's what we're going to reference there in the MS paper. We're also going to need to choose the fraction of features that are available at each split. If you're writing R code and using the standard random forest package in R, that's called mtry. In the Microsoft paper, that's denoted by the variable row. We also need to determine how many trees in our ensemble to create. So that's called ntree in R, or capital T in the Microsoft paper. Lastly, we need to decide on each of our trees, should we prune the individual trees or should we not prune? Often, instead of pruning, the trees are limited in their maximum size by the maximum number of nodes. And so in the R code, that's called variable that limits that or sets that maximum size on the nodes. It's called max nodes, or it's called D in the Microsoft paper. In the original Lee O'Brien random forest paper, when he wrote the first paper publishing this, he claimed that you don't have to prune the trees. The individual trees will overtrain in this averaging process and this great amount of variance that comes in, variety that comes in by doing the random subset selection of the features for the nodes, will create enough variance that will cancel out any overtraining from not pruning your trees. Generally, that's held up in practice, but it's often worth testing. So often people can make your random forest initially and then test to see if you should prune your trees. The only case where I can think of where you really surely want to prune them is if they wind up growing too big and they slow down your runtime, then you might want to set some maximum nodes just for computational reasons. Okay, so let's go through each of these parameters in a little more detail. So first parameter here is the bagging sample size. Remember, what does this bagging do? By taking a random subset of the data, we're creating variety among our trees, or we're decorrelating the trees. So a lower fraction is going to create more decorrelation. On the other hand, there's a trade-off at the extreme values. If you create an extremely lower fraction, you'll get individual trees that have lower accuracy. So we want to have a sample size for the bagging that's small enough to increase that decorrelation, but not so small that things become too accurate. So how do we select that bagging sample size? Usually cross-validation, or something which is called out-of-bag error, where when each tree is created, we can take the data samples that were not used in creating that tree, and we run those data samples through all the other trees, and then we average results. That gives us a estimation that's very close to cross-validation when you have a lot of data and a lot of trees. And so generally you can use cross-validation or out-of-bag error. And I would do this in 10% increments, going from 10% to 100%, but you could be more or less exhaustive on that search. But some sort of cross-validation, out-of-bag error sort of selection for those. Next parameter, how many trees do we want to create? And what is the effect of this parameter? So the more trees you have, the more accuracy you get, but up to a point. And typically, you'll get a lot of increase when you go from 1 to 2 to 10 or 20 trees, and then you'll increase more out to 100. But at some point, increasing doesn't give you any more accuracy. So that may be at 500, you don't want to create more trees, or at 2,000, you have enough trees. Depends a lot on how complicated of a decision you need to make, how complicated your space is, how many features you have, how much data you have. And so that's always done by some sort of cross-validation or out-of-bag error. I would initially test, just as a rule of thumb, from 1 to 1,000 and look at the plot. And we'll see that plots that are used for testing that. You graph the error as a function of the number of trees and figure out how many trees you need. And so the next parameter is the fraction of features available at each split. So remember, by selecting only some of the features for each split, we make our trees to be different from each other. Right? We're forcing them to be different from each other. We're creating more variety among our trees, or we're decorrelating the trees. And so this parameter that gives us the fraction is called mtry. In the R software, it's called O. This is probably the most important parameter that you're going to be tuning for a random forest. And the way this works, a lower fraction creates more decorrelation among the trees. So the trees are more different. But it also creates lower accuracy of the individual trees because they don't have as many parameters to select from for their classification. So there's a bit of a trade-off there. How do we select that? Of course, it's cross-validation or out-of-bag error. I would go in 10% increments from 10% to 100% if I was going to do this. Often, for classification, there's some like back of the envelope or just general heuristic rules that people use for classification. The general rule is to start with the square root of p, where p is the total number of features. So if you have 50 features, you'd start with the square root of 50 features for each split. For regression, the back of the envelope rule is start with p divided by 3 features for each node. But those rules are only general rules. If you have a lot of features that are highly correlated, you would need a different value there than if you have features that are all different. The next variable is max nodes, or the decision whether we're going to prune or not prune by tree size. Generally, it's a good rule of thumb that to not prune, and if you have enough trees, then not pruning is okay. And the idea here is that you want your trees to overtrain, and they're going to get really accurate on their training data. But that wouldn't for the individual trees wouldn't extend robustness, but it's your averaging that gives you your robustness. So if there's something that's sort of quote unquote overtrained in a lot of your trees, that's only going to occur if that little feature of your training is common, because you're taking random samples of your data and your variables. So the effect of deciding to prune or not prune, prune increases the accuracy of your individual trees, sort of. And when we say accuracy for your individual trees, that's like robustness or accuracy on test data. But we don't care very much in a random forest about your accuracy on your test data, because we're going to take averages of things to take care of that overtraining problem. So generally you don't prune, but certainly if I was working on a random forest for something I cared about, it was important, and it was a project I was building that was going to be used by somebody, I would try pruning, and I would try not pruning and see what gives me better cross-validation or out-of-bag error results. Okay, so let's take a look at these individual parameters and the analysis of them in the Microsoft white paper. Now, one of the things I like about this Microsoft white paper is it's written by computer scientists, and they are writing it for to be used in the Xbox Kinect. And so they're going to take they're going to do some analysis of just how robust or how do things perform on different types of data, in addition to the rigorous statistical motivation for predictors. It's good to look at this type of data. So this is the type of thing a computer scientist would do more than a statistician. And so it's a good complement to the things we've been taking a look at in our book. And so this first parameter is the sample size in R. And here's a plot from the random forest paper. The plot on the left-hand side, they've built their random forest using just randomized node optimization. So that's selecting a random subset of features at each node. On the right-hand side, they've done bagging with a 50% of the random data for each tree and random node optimization. And so what you see is in this picture, so let's review what these plots are showing us. There's two data sets, one yellow on the left, one red on the right. And the shading in the background is the probability for each of the classes assigned by random forest. So in areas here that are all red, that means high probability red. Areas here that are all yellow is high probability yellow. And we fall off from yellow decreasing, and then as you move from left to right, and then you would start it from a high probability red and fall off as you go right to left. And that's what this plot on the bottom is. The yellow gives you the probability of being in the yellow class as you slice across the data where this white dotted line is. And so we see the effects of bagging or not bagging in how much this transition across and then the sharp linear and then it comes across again gets smoothed out into a smooth transition in the probabilities. So bagging smooths out your decisions is a sort of a rough way to understand it, or that's the effect of bagging that we observe in this plot. There's a little bit of a discussion, which is also very good in the paper, about maximum margin, which is worth paying attention to when you read the paper. Next feature we're going to look at is the number of trees that we create. So this is called N-tree in R, or T in the Microsoft paper. And so in this plot, this is a figure from the Microsoft paper. The first on the bottom, what we have is decision regions for this two-class problem using the red and the yellow. And so this random forest, there's one tree, right? T equals 1. It says we're going to build a random forest with one tree, and with one tree we can make one split, yeah, right there. And that works perfect, and we don't need any more splits. And so we can see this accuracy is going to be 100%, but it doesn't give us a good sense of the probabilities and the drop for as you go from red to yellow. And so when we use 8 trees, we get some nice gray regions. And then when we use 200 trees, you see we've learned a sort of reasonable, right? That's the sort of 50% between red and yellow. And this is the maybe 75% red, 25% yellow. And there's like an area here that's maybe 75% yellow, 25% red probabilities. And so it learns the contours for the decision surfaces between classes better as you create more trees. Creating more trees also gives you more accuracy, which is what we have in this plot. So again, we're still looking at what's the effect of the number of trees, and we're going to talk a little bit about now how you choose that parameter. So this is a plot, and it's from Elements of Statistical Learning. And this plot is working on a spam data set. So it's trying to predict spam in email. And so horizontal axis is the number of trees, vertical axis is the misclassification error. In orange, we have the out of bag error, and then in blue, we have the test errors, or test errors test on our data set, on our test data. And you see, of course, as you start from 0 and you start moving across, there's a sharp decrease in error. So we get much better as we build a small number of trees. And the further we go, we still get decrease. And I'm not sure at what point you would declare we're not getting any more decrease. You know, maybe here. Maybe if I didn't care much about runtime, I might say, okay, let's take 2,000 trees, because after that I'm not seeing much improvement. So that's how you would pick. You look at a plot of the error as a function of the number of trees, and you'd say it's going to be decreasing up to some point, and what's that point? And that would tell me how many trees I want to build. And this is what we see here is pretty standard for the number of trees. You always have a sharp decline initially, or almost always, and then there's a longer period with a gradual decline, and then at some point you declare, okay, I'm close enough to being my asymptotic to my minimal error, and then I'll stop there. Next parameter to look at is the fraction of features that are available in each split. And so this is looking at a picture from the Random Forest Microsoft white paper. And so there's 3 plots here, and the difference is row is 50, and row is 5, and row is 2. And so this is higher dimensional data plotted in 2 dimensions. And so when you have a larger fraction, what you get are what you see here across the bottom. These are these probability curves as you take a slice across the plot on the white dotted line, and you get sharper distinctions versus these gradual blurring and what you see in the regions, there's broader gray areas as you decrease the fraction of features at each split. So we're getting more variety among our trees. That's going to make us more robust against overtraining, and it also creates more gray areas. Again, here we're still looking at the fraction of features available at each split. This is figure 8.10 from Isler textbook. And so this is on the, let's look at the data because this is kind of important. This is the 15 class gene expression data set with 500 predictors. So this data set has a large number of predictors. I think there's 18,000 predictors available in the gene data set. Oh, okay, sorry, this gene data set has 500 predictors in it. Gene data sets have large number of predictors. So this is one of these problems where you have too many predictors for the amount of data. Quite often, Random Forest handles this fine. And so here we're picking the value of mtry, or what's called rho in the Microsoft paper. So this is the number of predictors that are available at each split. And so we have plots of the error on the vertical axis as a function of the number of trees for 3 different possible values for the number of features at each node. And you'll see the orange, which has the number of features each node equal to the full features, right, in the plot. It's right there. That's just doing bagging. That's not a random forest ensemble, it's just a bagging ensemble. And then the random forest ensemble, which has shown in green where m is the square root of p, that's down here, and that's giving us the best error. So orange is really just bagging. The green is a random forest. The blue, m is p over 2, which would be 250. So we're really not getting a benefit at the point of p over 2. It's really, you have to decrease p, you have to decrease the number of features available at each node down to square root of p, and that's going to give you your best error. I would try a bunch of these if I were building this random forest, but then the plot would get messy if you put them all on your plot. So this really shows that the benefit from taking those random subset of your features for each of the splits in random forest over bagging in this example. Last feature or last decision in making random forest, do we prune or do we not prune? And so I mentioned if you build enough trees, usually pruning or not pruning doesn't matter. That's the sort of heuristic general rule, and in my experience, that's been true. But here's a results from random forest with d equals 3. That means that the number of nodes in the decision tree is going to be 3, and they observe underfitting. And then d equals 6. They seem to like d equals 6. It gives them something that seems to be decision boundaries that are good. And you could look at particularly this area here. That's kind of a complex decision boundary. Maybe, really, there's a couple of complex decision boundaries where the classes meet and sort of overlap. So there's a complex decision boundary. And you could say, do those contours really match what I think they should? And they, in the paper, they say d equals 6 seems to be working well. In d equals 15, these places are circled. The authors are saying this looks like overfitting or overtraining. I think I'd agree with the authors, although generally, if you take enough trees, you would be likely to see that go away. But it's one of those things that's worth testing on different data sets. So there's tree depth. Another nice advantage, this is really a big advantage, a nice effect of using a random forest. Every time you make, so the thing that you get here is called variable importance, and it tells you how important your individual variables were in random forest when it makes a decision. And the way you compute variable importance, you look at the mean decrease in node impurity for each split on the variable. So when a split's made on a variable, when that split is more useful in creating the forest or creating the tree, then the importance for that variable goes up. And so this is variable importance for the heart data. And so we see the most important variable is this thal. And so these are from blood tests, and then CA, and then next comes chest pain, which, of course, when we think about heart attacks, definitely chest pain should be important. And so we can see some of those most important variables, and then as we go up, they become less important. And that means they were less useful in making splits that increase the purity in each tree. And in this tree, it was the mean increase in Gini index, but it could be increase in Gini index or entropy. Either of those can be used as a measurement for node impurity. Let's talk about some empirical advantages to random forest. This is really a big deal. Random forest can handle continuous data or class-based or quantitative or class-labeled data, right? True, false, up, down, male, female, things that are difficult to manufacture, the name of the manufacturer for state something comes from, etc. They're difficult for k-nearest neighbors because you have to build a metric, or linear regression. They have to be sort of modified and handled. But random forest handles those just fine. You make your splits to say, send everything with a class label of A down one side and class label of B down the other. The other thing that random forest works fine with, and this is important, is extreme distribution. So you could take your data and transform it in anything that's a monotonic transformation, meaning as long as you don't change the order of the value on your data points, you could modify your data, your individual variables, and you won't change the random forest result. So you could take your data and you could square it, square one of your variables, keeping the sign, and you wouldn't change how random forest would build its forest. So correlation. So correlated features have limited impact because they're used one at a time in tree growing, right? So correlation is a hard thing for linear regression to handle. Multivariable linear regression, if there's a lot of correlated variables, it causes problems, but not for random forest. The only impact of correlation is that if you have variables that are correlated, you have to take your random subsets so that you get sufficient variety and utility out of your variables. So you may pick slightly different parameters if things are correlated. Feature interactions. So you can have things like this. So if feature A is large, then feature B becomes important. But when feature A is large, feature B doesn't matter. There's interactions between your variables you don't get in linear regression or generalized additive models. So trees are good at handling these things, and random forest can handle them and handle them robustly. Another way to express this is the decision boundaries between classes or the types of relationships that random forest can learn in regression aren't linear. So there's no restrictions on linearity for random forest. Feature selection. Features that have low utility don't get used much, and so they don't impact the results very much. So with linear regression, we saw we get much better results when we drop some features. If they're not useful, random forest will drop them automatically, as long as they're not dominating. As long as there's not too many of them, they'll get dropped automatically. The small n large p problem. So if you have data sets that don't have a lot of data observations in comparison to the number of parameters, so large number of predictors, small amount of data, that causes problems in a lot of classifiers, particularly in linear regression, but random forest doesn't have a problem with it since features are only used one at a time. So, okay, review random forests. Random forests are a way to create an ensemble tree predictor using bagging and then using these random feature selections for each node. We've talked about a lot about sort of what goes on under the hood, sort of different ways you can see why they're useful. So why is this a good thing? Individual trees have overtraining, but then we take the average using the randomness. It makes up for the overtraining, at least in large part. And to say this in sort of statistics, we decrease the variance error, but we don't affect the bias error. We're not injecting any bias into the system by assuming that the relationship between x and y has any specific structure, but we decrease the variance error by taking the randomness and the averaging. Also, there's effectively no assumptions on separation surfaces. Separation between different classes doesn't have to be linear. And we also get some nice side benefits, the out-of-bag error from bagging and variable importance. Thank you very much for watching.